questions during the talk. That really helps. It helps me out if there's a few questions as we go along, but I don't want to run too long, so I don't want to take too many during. Okay, one of the very exciting things about this supernova was that it really taught us a lot about how they worked, particularly just because it was so close to us. It was only in the Large Magellanic Cloud, that's 50,000 parsecs away. And so one of the really awesome things about it is that this is the 1980s. By then we had neutrino detectors operating, and their main purpose was, they had a couple of purposes, but one of the main purposes was to look at neutrinos from our sun, coming from the fusion processes in the core of our sun. But when 1987A went boom, these two neutrino detectors saw between them a total of 19 neutrinos. And if you calculate, okay, you've got a point source emitting neutrinos probably in all directions equally, and these detectors are very tiny, very far away, right? So they intersect a small amount of the outgoing sphere of neutrinos from the explosion, and they count 19. If you extrapolate that over the entire, surface area of a sphere at the radius of, the distance of the supernova, how many neutrinos did the thing emit? How much energy does that correspond to? You get an enormous amount of energy, 3 times 10 to the 53 erg. So that's a few hundred times the total energy that our sun will put out in its lifetime. About 0.5% of that energy, so that all of that came out in neutrinos, and then from observing the explosion, with optical telescopes, you can measure the expansion of the, the star itself and see how much kinetic energy it had, and it was about 0.5% of what came out in neutrinos. Now the neutrinos arrived 3 hours before the optical supernova because they're streaming straight out of the center of the star. The rest of the star barely, absorbs any of them. So that, being neutrinos, they're weakly interacting. They just fly right through the rest of the star. So you see them first. You don't see the optical supernova until the explosion works its way through all the outer layers of the star. So that's where the 3-hour time delay comes from. Today, we've got bigger and better neutrino detectors online, and in fact, the April speaker, Professor Karagiorgi, she is very interested in searching for neutrinos from future supernova explosions nearby with the detector she's working on building. So, okay. So we should all wish SN 1987A a happy birthday. It's turned 30 just a couple weeks ago. This is a set of images from the Hubble Space Telescope in the optical, showing you how the appearance of the supernova has changed over time. Went off in '87. Hubble didn't launch until 1993, '94, and it's been tracking it periodically since then. So you can see as the shock wave from the supernova expands, it lights up the material in surrounding space and heats it up and causes it to glow. And so you see that ring around it getting brighter with time. This image on the right shows, I guess this ring corresponds to this ring here. The smudge in the center corresponds to the smudge there. Somewhere buried in this smudge may be the compact remnant that SN 87A left behind. We have not been able to find a neutron star, a pulsar, or any evidence for a surviving object. So it may just be that it's hidden beneath a layer of dust in there, and we haven't found it yet. So 87A was a blue supergiant star before it exploded. So that meant it had gone through a number of stages of its evolution, and it had thrown off various outer layers of material. So its surroundings were very complex and inhomogeneous. And as the blast wave of the supernova expands, it's gradually encountering different layers of that material. And so it, first encountered this material and lit it up, and now it's expanding outward further. And you have to remember this is a 3-dimensional object that we're seeing in projection on the sky, just measuring it in 2 dimensions. And so these other rings have more recently shown up at a greater distance from the progenitor star. Okay, so what I personally am very interested in, all of this